So this is a fun little circuit. It's a relaxation oscillator, which is really just a capacitor going to charge and discharge over and over again. We're going to use the output of the comparator as it changes states to accomplish that. So when the output of the comparator is high, we'll have a charging path. That's what we need the 1K for. And then when the output of the comparator is low, we'll have a discharging path. To set all this up, we have to do a couple tricks, and one of the main things we're doing is adding positive feedback. That's what this is called when you take a resistor and connect the output back to the plus input, the non-inverting input. So this is known as positive feedback, and it does a couple things for us. It actually creates two thresholds for the capacitor, and we'll follow all this in a minute. And those two thresholds, there's a difference between them known as hysteresis. And so we'll talk up through all that. But those are some of the big terms. The positive feedback creates hysteresis for us, and that enables the relaxation oscillator to work. You can't have the cap charging and discharging to the same level. That would just be a real high frequency. As soon as it's over a level, then it discharges down to that same level, then back over that level it charges. And I think you could see that, but we'll try to illustrate all of that for you. So, so it's called a relaxation oscillator because the capacitor charges up and then discharges. So let's pick a starting point and we can try to see if we can understand the whole circuit. I guess the capacitor initially, it's going to just have 0 volts, right? So let's think what will happen. When the cap has 0 volts, can you see the minus input for the comparator is basically watching the voltage of the cap. So which input's going to be winning? Well, we might not be totally sure of the voltage, the reference voltage that's sitting here, but if this is 0, it's a pretty good guess that this is going to be winning. So the output's going to be high, right? And we can put that over here. And we know what that means internally to the comparator. When the output is high, there's this little NPN transistor switch that'll be open, right? So not much is happening at the output other than just an open. And that's why we need this 1K resistor. This is kind of like our pull-up resistor, if you remember it. We had a 10K. We reduced it to 1K because we actually want it to be pretty much insignificant. And so it'll sit there and it will provide a way to charge the cap because the output of the comparator cannot do that. It's just an open. Later when we do this same trick with op amps, we would have a connection to the plus voltage right here. But the way the comparator that we have works is it's just an open. So here we go with the comparator open. We know it's a high, and that's your FET that you have connected here will be on, and the lamp will be on because we can use a lamp on the output to see what's happening there. You can leave that part of your circuit all connected. So the 1K provides a charging path while the output's open, and here we go. Current will charge up, and we can sketch that in if you want to see that. When the output of the comparator is high, there's an open here, and the charging current will flow onto the capacitor, and it'll charge up. How far will it charge? Well, that depends on this voltage here, okay? So let's try to see if we can get to that voltage, figure that out. This is our reference voltage, right? That's the voltage the comparator is using to compare where the capacitor is at. If the output is open here, that doesn't really affect this point. But again, we have more or less a straight connection to the positive voltage. Again, we're trying to make the 1K insignificant. That's why we're using these 100Ks, large values here. So if you think about it, the 1K is not a big deal. We can approximate it to 0. If you wanted to split hairs, you could factor it in. But let's get the big picture here. Do you see our voltage divider here would split whatever voltage we're running the circuit on, it would split it right in half and give you half the voltage for V reference. But when we added the feedback resistor, this positive feedback resistor actually creates a series parallel circuit for us. Do you see that? Because if you can approximate this end of R5 as being right at V plus, that's an okay approximation. This is insignificant, pretty much. But picture that point being plus 5. Do you see that R5 and R3 are in parallel? They share this point, and they essentially share the plus voltage point. So R3 and R5 at the moment are essentially in parallel, and that equivalent resistance is in series with R4. So if we look at that fact, I think you can see the reference voltage that we would expect, right? And again, if you want to, we could couple these sort of, what is that equivalent resistance? 50K, right? It'll just drop right in half. And the 50K is sitting in series with 100K. So can you see the reference voltage at this moment will be what, 2/3? 2/3 of whatever voltage you put there. If you want to, we can put some actual voltage there if that helps you wrap your head around this. So I think we're going to try powering it up with 6 volts just so that we have a nice easy number. So our reference is going to be 2/3 of the 6 volts, right? So we could put 4 volts here, right? That's what'll be sitting there at the plus input. Yeah, 2/3. What does that mean? Well, the capacitor is charging, remember, while the output's high. And while the output's high, the reference voltage is 4 volts. The capacitor will charge up to 4 volts, and as soon as it becomes greater than 4 volts, then this input, the minus input's winning. You remember what happens when this input wins. So as soon as the capacitor goes past 4 volts, the minus input wins and the switch closes, right? And so now the output goes low. Of course, that turns off the FET and the lamp turns off. And this low is actually a connection to ground, and you see that the capacitor will now start to discharge. Okay, so we now have a discharge path to ground for the capacitor. So again, as soon as the capacitor charged up just past 4 volts, right? It was rising, it was charging, and as soon as it got to 4 volts, as soon as it got greater than 4 volts, just a little past 4 volts, the comparator switches the output state to where this switch is connected to ground, the output goes low. The cap is now discharging. To where is the question, right? This oscillator would not work if we had a fixed 4 volts here, because the capacitor would charge up to 4 volts. As soon as it goes past, it was discharged till it went below 4 volts, and then it would charge back up above 4 volts, and so on. And it would keep repeating that very tight cycle. Do you see what that does if you have a single threshold where the cap initially charged up to the 4 volts, and then, oh, it went past. So now it's going to discharge, charge, discharge, charge, discharge, charge, and you just have what looks like a lot of noise. It'd be a very high frequency oscillation, basically looking like noise, because as soon as you go over, then you go under, then you go over, and so on. So this is the part that we have to understand is important. If you're going to build a relaxation oscillator, you're getting close here, but the other thing to understand is this reference voltage has to change, and it does because of the positive feedback that we added. That's why R5 is so crucial. If you just parked a certain single reference voltage here, the cap would go above and below it, yes, but at a very high frequency, like we demonstrated over here. So look what's happening. The series parallel circuit is going to change when the switching action occurs for the output of the comparator. Do you see when the output of the comparator switch closes? It now connects this point to ground. This point to ground means that R5 is now in parallel with R4, not R3, right? So when it goes low, let's draw that. Our new relationship for our series parallel circuit of R3, 4, and 5. Let's get that set up here. Let's get this off. Yeah, and let's show you the new relationship. Is R4 in parallel with R5. And again, we picked numbers that are nice and easy on purpose. 100K and 100K in parallel. Now we've got the 50K here that's in series with the 100K. And you see the new reference voltage is going to be the voltage division that occurs between the 100K as it sits in series with 50K. So you're only going to get 1/3 of the 6 volts here. So let's fix that. Our original reference voltage, we could put it, let's put it here, let's put it up here, was 4 volts. And now the new reference voltage when the output goes low is only 2 volts. And this is perfect because now the capacitor has to charge up to 4 volts. As soon as it goes over 4 volts, it starts to discharge, but it has to go all the way below 2 volts. That's the hysteresis, the two thresholds. The distance between the two thresholds is known as hysteresis. So you use positive feedback, which creates a series parallel configuration that switches when the output switches, and that switches the reference voltage from 4 volts to 2 volts and back and forth. And that gap, that distance between, that no man's land, or the hysteresis is what you would call it technically, is what's important to create any relaxation oscillator. So let's take a look here at our things, maybe graphically, that we've established. Initially, the capacitor charges all the way up to 4 volts, and then the output changes and connects the capacitor to ground essentially through R1, but it provides this discharge path to ground. Yes, some current's going to come along for the ride through the 1K, just like it always does with a pull-up resistor. That's also going to be a current. We don't really care about that. That's just current that's thrown away. But the cap's going to be having a discharge path. That's the one we care mostly about. And that'll happen, like we said, the cap's going to charge up to 4 volts, at which point the minus input is now winning, so the switch on the output of the comparator closes and starts to discharge the cap. But the closing of that switch also caused R5 to be in parallel with R4, not R3, which changed the reference voltage to 2 volts. So the capacitor has to discharge down, not below 4 volts to change the output of the comparator, but all the way down below 2 volts, because that's the new reference voltage. So the minus input is still winning, even when the capacitor is 3.9, 3.8, 3.6, 3 volts, 2.9. As the capacitor drops, it's still winning here because the new reference voltage is 2 volts. So it has to drop below the 2 volts for the output to change and go high with this output NPN transistor switch open, which allows the cap to charge. So it's 1/3 and 2/3. 2/3 of the voltage and 1/3. The capacitor charges up to 2/3 and down to 1/3. Now, as soon as it goes below the 2 volt reference, which is 1/3 of our supply voltage, as soon as it goes below that, I think you can see, then this input, the inverting input, the minus input, is not winning anymore, right? As soon as the capacitor discharges below 2 volts, then the plus input's winning. When this input is winning, the output goes high. The switch opens up. It goes high because of our pull-up. And also that pull-up is what we need to provide a charging path for the cap. Nice little trick. And then so it just repeats, so the capacitor dips below 2 volts, the output switches state, so does the reference voltage. It's not 2 volts anymore, it's 4 volts. So the capacitor is always chasing after our new reference voltage. Okay, and this is the relaxation oscillator. Charges up, discharges up, and discharges continuously. How fast depends on a couple things. Depends on the charging resistor, depends on the size of the capacitor. So you can vary these and you'll get different frequencies. You can start off real slow and get a real nice visual on it happening in real time. You can speed it up. You can change the flashing rate of your lamp essentially. And the other thing though that affects the frequency of oscillation is the hysteresis. So I mean, you could change R5, and right now we just kept some real easy numbers to see what's happening very easily without having to bring our calculators out. But the more positive feedback you give it, which means you would lower this resistor, that means the more impact you have on this voltage division. So you could get even a wider gap between your two threshold voltages as you increase the positive feedback. I mean, if I took this down to like a 10K resistor, it would slow things down because the capacitor, the distance between the voltage that it has to charge to and discharge to would widen. Because think about it, as I lower this resistance, I'm having more of an impact on this voltage division as R5 is in parallel here and then here. A 10K has a lot bigger impact than 100K. Or if I went the other direction, if I went to 1 megohm here, I would have less impact on the voltage division that is providing the reference voltage. And so the hysteresis would narrow, and the frequency would speed up, right? I mean, the hysteresis, if it was in here somewhere, then the cap only has to charge up to here and down to here and up to here and down to here. So the frequency goes up. Or if I spread the hysteresis wider, a wider gap between those voltages, if I went to 5 volts and 1 volt, it just takes longer for the cap to get all the way up to there and then all the way back down to here. So this frequency would slow down. So your positive feedback actually sets the gap between the two reference voltages. That's known as the hysteresis. That does have an impact on the oscillator frequency. But the big things you could probably play with easily, I mean, you could maybe leave this and just play with the charging and discharging resistor because it acts as both. And yes, this is in the charging path also, but we try to keep that more or less insignificant. But it's there. If you want to factor it in, you could count that in. And then, of course, your size of your capacitor determines, of course, how long it takes to charge up. If you have a larger capacitor, it'll take longer to charge up, as we've seen before. So I think we've kind of run through everything. You can put your oscilloscope channel 1 and channel 2 right on these inputs, and you'll see the capacitor, charging up. You'll see the reference voltage. You'll see the reference voltage start high, and the capacitor's rising up to it, right? And then as soon as the capacitor gets there and crosses over, the reference voltage is going to change. So the capacitor has to chase now the new reference voltage, which is down here. The capacitor will be chasing that after that. And as soon as the capacitor gets below that threshold, the output of the comparator changes. It goes high, and so does, and the reference voltage also changes. And so the new threshold the capacitor has to chase is here. So you get this kind of a look. Whoop, and as soon as you go past it, and so on. So your reference voltage, you'll see with the original numbers, and powering it with 6 volts, you'll absolutely see the reference voltage automatically changing to make the capacitor charge to 4, and discharge to 2. Charge up to 2/3 and discharge to 1/3. So that's a nice look. You could, if we had a third channel, you could be watching the output going high and low. That'll be happening as well. You'll get like a 6-volt and a 0-volt square wave out of here at the output. You'll certainly get to see the FET turning the lamp on and off at whatever rate you choose. And probably choose the rate with R1 and C1. You can leave this alone for now. If you put a variable resistor here, you certainly can, and you could put a variable resistor here also to really, dial stuff in however you want. Be careful if you put a variable resistor here. You mustn't ever let it be 0 ohms. You'd probably want to put a fixed K in with the variable resistor somewhere in here. Picture if you had 0 ohms here because you turned the variable resistance all the way to 0. This cap would blast a high surge current down through the transistor switch and blow out your comparator. So you have to never allow this discharging path to be too low. 1K would probably be, as low as you'd want to go. So, but yeah, you can play around with all these variations if you want. It's true if you start getting low in your resistance values, this R2 becomes not as insignificant as it is in this current setup. I mean, if you start to lower some of these values here, maybe the 1K is not as insignificant. So that's why we kind of kept these kind of where in the neighborhood of where they are in the 100Ks, because we're trying to idealize this to sort of a 0 effect on everything. Okay, I think we got most of the main points. Let's see if there's anything else. Yeah, but it's a cool circuit. It certainly hits a lot of the things that we learned in the DC course. It's a nice little demo circuit to pick up on our new knowledge of a capacitor charging and discharging, but it's kind of fun. We can create this little circuit that does that automatically, known as an oscillator when you get into something that repeats like this. And one of the main mechanisms that makes it all possible is a simple little series parallel circuit here. Okay. We'll probably do this again when we get to op amps in the spring, and it's essentially the same effect. And at some point, you don't always explain it as the series parallel circuit that it is, although I like having that level deeper understanding. I think a lot of people just know it in terms of positive feedback. That's what that is. How much positive feedback do you give it? How much hysteresis do you want? But it's cool. From the DC course, you can understand that a level deeper. You know that it's actually just a little series parallel voltage division going on to vary the reference voltage. Okay.